MRI gradient coils. Okay, so much for those. And what we now want to do, now you have learned the difference, or at least you know there is a difference between a gradient field and a field gradient, okay? And the field gradient is constant in magnetic resonance imaging across a long space. What I now want to do is I want to take a somewhat more formal look at why we can measure position in magnetic resonance. And the key feature is that in NMR we look at magnetization, we take a radio frequency field, we rotate the Z magnetization to the x-axis, and then we turn the B1 field off and the magnetization starts to precess around the Z-axis. And the precession means it acquires, as a function of time, a certain precession angle. That angle I call phi. And the whole story about NMR is measuring that precession angle. That's the fundamental thing what we do in NMR. We measure a phase, the angle we call a phase. And that's why we call NMR a phase-sensitive method. X-ray scattering cannot measure the phase of the signal. It only can measure magnitude. And that's why with X-ray scattering you cannot measure phase-sensitive images the way you do with NMR. So there's that difference I want to work out. So our NMR signal, and we've seen that before, is our transverse magnetization, initial magnetization, then there comes the exponential function that has a relaxation term and the precession term. Now if the precession frequency for whatever reason depends on time, and it does if a spin diffuses or moves in a magnetic field that has a gradient, so it varies from position to position. So it moves along, let's say by flow through a pipe. It has one precession frequency initially, and as it moves along, the precession frequency changes. So we have to look at a precession frequency that changes with time. So if that is the case, then instead of having frequency times time, which is exactly that angle, we write for the angle the integral of the frequency over time. And the frequency, the fundamental equation for the frequency means that the frequency is equal to gamma times the off-resonance magnetic field. So the NMR frequency is proportional to the strength of the magnetic field. The fundamental equation of NMR. That you also need to know. So now we write the precession angles as the integral of that off-resonance magnetic field. And if we plug that into here, into this equation over here, we come up that our transverse magnetization, so that initial magnetization, the relaxation term, and there now is the integral of the precession frequency over time. And what we do in the following, we write that sum in the exponent as a product of two exponents. We take the attenuation term, we write it as a of t, and here we just have an exponential with the integral of the precession frequency over time. So you may say, well, what did we gain from this? We gain from this that we now can look at that integral of the precession frequency. We can look at the phase and describe that in terms of this integral. And let me move on to the next slide. No, that button here. Here is our picture again with the phase. And we know the phase is given, that integral of the precession frequency is given by the integral of the off-resonance field. Now that magnetic field may actually not be just linear. In the general case, it may also be curved. It may have some arbitrary form. How do you express a function that has an arbitrary form and you want to express it in the vicinity of a certain point? You use the Taylor expansion. Do you know what the Taylor expansion is? Do you know that from mathematics? Who knows the Taylor expansion? Who has heard the word Taylor expansion? Some people have. Okay, good. I hope the others have too. They were just too shy to say yes, or you may not remember. So a Taylor expansion is you take the derivative of the function and multiply it by the parameter, and then you take the second derivative, etc. And that's what we do with the magnetic field. So since we don't know what the magnetic field looks like as a function of space, we expand it into a Taylor series. This is the first derivative, that's the gradient, and that's the second derivative. So the gradient field is that linear variation we say of the magnetic field with position. Now position I just call R because I do it in one dimension to keep things simple. And the quadratic term here, the second derivative, that's the quadratic expansion coefficient, would be this function over here. Call it R squared. Now the second thing is what we need to do. We have the position in here. That's the position of the spin. Now if the spin moves, it also has some arbitrary path it takes. We don't know which path it takes. So what we don't know, when we don't know the path, what do? We do a Taylor series expansion of the position of the spin, how it moves. Now we do that Taylor series expansion, we get the initial position times the velocity times the acceleration times time. So we get that, probably this you know from high school physics. The position of a particle is the initial position, the velocity term and the acceleration term. They add together. That's what this expression means. You can do this the same thing for position square. Actually you can square that and sort terms and then you arrive with that expression. Now we have three Taylor series expansions, three sums. So there's the first sum, and that one here is this sum, and this term is this sum over here. And this is a lot of stuff to plug in, right, and to sort out. But that's what we need to do. And when you do it, you come up with the table that I show you, which has just a sum of phase terms. Now we say that this phase for the magnetization is the sum of all these integrals. So we started out by saying the phase is the integral of the off-resonance field or the integral of the precession frequency over time. And that integral now breaks down into an integral that has the gradient in here as a function of time, with time to the power of 0, to the power of 1, to the power of 2, and it has a curvature in there again with these powers, and there is the position, the velocity, acceleration, and there are some other terms in there. Now that's a complicated thing. The total phase is a function of these, we say, gradient modulation functions. The gradient modulation function is we turn the gradient off at a certain time, we turn it on, we turn it off, we turn it on, we turn it off. Or we shape it, we give it a certain function. How, as a function of time, we vary the gradient, the additional magnetic field that does our space encoding. And we learn from it, when we modulate this function, then we learn where the particle is, because both of them, the product of this function times the position, gives us the phase of the NMR signal. And we say that these two parameters, that integral multiplied with gamma, times the position, we call their Fourier conjugate variables, because both together give a phase. Like frequency times time gives a phase. And now we have here a position, and this is a term that makes position times time a phase. So this is actually, when you look at the water wave, you see it as a function of space. You know position where it is, but then there must be the other parameter, which we call the wave number. And that's the wave number is a term that you're probably familiar with from infrared spectroscopy. The wave number is that integral over here. Both together multiplied give the phase. And the wave number is called K. That's a nomenclature that Peter Mansfield has introduced. You probably may know the term K also from X-ray diffraction or from neutron scattering. People also discuss K. It's again the wave number. It's the same thing which we encounter here in magnetic resonance. So we have these same terms, and when you want to measure velocity, then you have to have the gradient modulation function multiplied with time and take the integral. And that's the Fourier conjugate variable to velocity. We call that Q. Now there's also Q is also used for scattering experiments. Some people use K, some people use Q, and sometimes it's just mixed and we don't quite know how to separate the two. And so you can go on with this. What we do in the following, we will cancel that part because there are very few experiments where magnetic fields are quadratic, and people use NMR with quadratic magnetic fields. There's some very recent work by the people in New Zealand that Paul Callahan started the team, and they use at these fields, we look at those fields with the NMR mouse, but that's very special. Typical imaging uses this case, so we only look at the phase contributions to the total magnetization phase when we vary the gradient in such a way that we can encode position, or we vary it in another way to encode velocity, and that means we get phase contributions, either this term or this term, to our total phase which we measure, the transverse magnetization which we measure, so that we can learn from the phase of the NMR signal where a particle is or with which velocity it travels. That's the concept. So this is a slight excursion to that, and I want to show you now what we have to worry about. What do we do with the gradient if we want to learn about position? How do we modulate it? How do we turn it on and off? And these concepts I will explain in the following. We have a simple way of saying if we want to encode position, then this is the gradient, there is time, and for a certain time we turn the gradient on and then we turn it off again. So in other words, we take these gradient coils in the magnet, which is actually a coil that has the current flowing in this direction and the other coil has it flowing in the other direction. If you have a Helmholtz coil, they both flow the currents into the same direction in the two coils. And an anti-Helmholtz coil has the currents, can I do this? This way and this way. Maybe that's right, I don't know. Now I get confused. This is difficult to do. You can try at home. And so that's what generates a gradient field. And so you turn that on for a short time, and when you do that, we know that our wave number k is just the integral. There's time to the power of 0 actually in here, so that's 1. So we have to form that integral, and the integral means that as soon as we turn the gradient pulse on, then that number goes high, and it stays high afterwards. So we have encoded we have turned on the Fourier conjugate variable to position. Now, if we want to know about many positions, let's say n positions in an image, we have to have n encoding steps, n different values of k, and then we have n equations for the we have these n equations for the phase for the phase of the NMR signals with n known values of k, and we can solve that for the position. So mathematically, it can be inverted, and we get the positions of the spins, which means the image where the spins are. And that's the formal principles. Now, you can ask yourself, how do we encode the flowing spins? And the idea is simple. One simple gradient pulse tells us the position of a spin. If we take two gradient pulses, then we have the final position of a spin that's now moving. A spin package flows through a pipe. We take the final position, and then we subtract from it the initial position. We take a negative gradient pulse of the same magnitude. And this is exactly how you measure velocity. If you want to measure the velocity of a bicycle that passes you, then you check the initial position, and you press your watch and you see how much time it takes to reach the final position. You take the difference between the initial and the final positions. That's the distance the bicycle has traveled during the time when you clicked your stopwatch. So we need to know the time it takes between the two gradient pulses that mark final position and negative initial position gives us position difference. That's the principle of that. And that function now we have to calculate from that the total wave number for position, and you find out if you calculate the total integral across these gradient pulses, then that integral is g of t prime dt prime. That is, the total integral goes negative and then it goes to 0. So there's no position encoding. You only learn about the distance it has traveled. And if you talk about q, the wave number that was defined in the slide before, then you take the gradient modulation function times time, and q now has a finite value. So if q has a finite value, that's the Fourier conjugate variable to velocity, then in this way you can encode velocity by making sure you switch your gradient in such a way that q has a finite value and k is 0. So the trick is, what are the ways to switch the gradients on and off? And typically one does that in pulses, turn on, turn off, and vary the amplitude of the pulse, so that either k is not equal to 0 and you code position, or q has a certain value and you can learn about velocity. Or you want to learn about both. You want to learn about velocity and position. That means you want to know at what a position does a particle have a particular velocity. We call that a velocity image. Then you have to modulate both. So the trick is, before we have done it in spectroscopy, we have always varied time as the Fourier conjugate variable to frequency. And here we vary the gradient as the Fourier conjugate variable to either position, or that would be the wave number, or we vary q, again a function of the gradient, in order to learn about velocity. So the concept, it's probably hard to understand how that works. The key idea is, let me go back, I see some faces that I think some of you are lost, so let's go back. The key idea is we look at the transverse magnetization, how it precesses, and we know that the precession phase can be expressed as a function, as the sum of all these terms in the matrix. In fact, there is even the term omega times t, precession frequency in the homogeneous field times time. That would be the case for spectroscopy. But now I only look at the water resonance. Humans are mainly water, we're 80% water. So the large signal in MRI comes from water, and we can go in the rotating frame and make sure that we are sitting at the water frequency, and that term goes to 0 because we are precessing with that frequency. And the off-resonance terms remain, and these are these terms. So we have phases. If we have a gradient across the object, a constant gradient, then we can learn about position with we call that the 0th order moment of the gradient modulation function, time to the 0. That's the 1st order moment of the gradient modulation function. That's the 2nd order moment of the gradient modulation function. So from the moments of the gradient modulation function, we can learn about position, velocity, acceleration, etc. So there's a very rich field what one can do by NMR with gradients. And here's a very simple scheme how to do that. You have one gradient pulse and you learn about position. You have two anti-phase gradient pulses, an anti-phase pulsed field gradient pair. That's how people call it in the literature. So final position minus initial position divided by the time between the two pulses gives us velocity. And now how do you do acceleration? You take final velocity minus initial velocity and divide by the time between the two pulse pairs. That's acceleration. That's velocity change. Velocity change is acceleration. And it turns out that actually this scheme, those people, has anybody studied of you numerical differentiation? How to program differential equations on a computer? It's exactly the same scheme. And the funny thing is, so if you ever do that, then you will find there's a very close analogy to finite difference calculations in computer science with pulsed field gradient NMR. It's actually quite a beautiful thing, because you can go to computer science books, to a numerical analysis, and learn how to write pulse programs to do imaging and sophisticated magnetic resonance experiments. That's a little side message. And let's go to more practical purposes. Let's say we have a very simple spectrometer. We have one that only gives us a gradient field that is constant over time. So the gradient should be constant, the magnetic field should be linear, but as a function of time we cannot turn it on and off because we don't have these power supplies and sophisticated machine. Then you can still work with pulsed field gradients, because you can use a stimulated echo. You can generate an echo with 3 pulses, a 90, 180 degree pulse, which give you the classical Hahn echo. But when you split the 180 degree pulse in 2, then you generate with the first one transverse magnetization, flip the magnetization down, precesses. You flip it back, then it becomes Z magnetization, again Z magnetization. It doesn't precess. And then you flip it back down and you generate the echo. Now what happens is that the gradient, the magnetic field inhomogeneity, is only visible to the spins when they're precessing, because it affects the precession frequency, not the value of the polarization in the z direction, because the gradient is way too small. So that means the gradient only becomes active while the magnetization is in the transverse plane. So I can write an effective gradient which is only active while the magnetization precesses, so only in this interval and after the last pulse. Now you wonder, why is that negative? Well, because these two pulses together give a 180-degree pulse. And the 180-degree pulse, I've plotted this here. I have transverse magnetization. It is here at the time we do a pulse along the x-axis. Oh no, it is here, the gray one, that's the initial one. This is the time before the 180 degree, the magnetization before t minus the 180 degree pulse. We do a 180 degree pulse, we flip the magnetization here. Now what we have varied is only the y component of the magnetization, but the x component stays the same. So if we go to how we express the magnetization, the transverse magnetization before the pulse, z to the I omega t minus. That's cosine omega t minus minus I sine omega t minus. We only change the y component, so we change the sign of the sine component. So it becomes minus. So after the pulse there's a minus sign here, and that's the same as if the magnetization had precessed with a negative frequency before, or with negative time. So it means the sign of the gradient, because the precession frequency now looks, after the pulse, looks as if this one had precessed in the other direction. So it's sort of a change of history. We rewrite the history book from the present now, because we know there was a 180-degree pulse. History looks different. Instead of positive, it's negative, or instead of negative, it's positive. Politicians like to do that. You can do that with NMR. And so you get the negative, effectively a negative gradient, and we can talk about effective gradient fields. And that is a very helpful way to analyze and learn what actually Q and K and the wave numbers for position and displacement look like. Now there's one more thing to the interpretation of the wave number. Why is it called a wave number? And this is the answer. I mean, there has been a question actually given to me, puzzled me also a lot. If the wavelength of the radio frequency wave that we do NMR with is several meters, how come that the resolution of an image is better than a millimeter? I mean, that shouldn't be possible. There should be a diffraction limit, right? It shouldn't be possible. But we're looking at the wrong wavelength. We need to look at the wavelengths of a magnetization wave in the sample. And here is the magnetization wave that becomes important. We have the magnetic field now in this direction, and we have the gradient here. So along position, the magnetic field is low, and with increasing position it increases. So we have a positive gradient. Now we look at the magnetization after a pulse. When the offset field is 0, the magnetization doesn't rotate in the rotating frame. When the offset field is small, it does a small rotation in a given time. When the offset field is higher, it does a bigger rotation in a given time. So the precession phase is larger when the offset field is large. And this precession phase increases with the value of the offset field and the time given for the magnetization to precess. So if we take a snapshot after a certain time about the precession phase, then we see it forms a helix that winds along the direction where the gradient is applied. And we can project the helix, that is, we look only at the, at the Y magnetization, then we get a cosine wave over here. Now any cosine wave has a wavelength. Actually it has a frequency if we look over it in time, and it has a wavelength when we look at it as a function of space. Now that's position here. So we have a wavelength, and the wavelength is just the period of that wave, of that magnetization wave. And that period is, we know it's lambda equals 2 pi over k, and k is the wave number. That's general spectroscopy, it has nothing to do with NMR. This is common knowledge, but we also know the phase is the wave number times position, and we know from our previous consideration that the wave number then is this integral. So the wave number can be expressed as the integral of the gradient over time. And that leads us to a very interesting comparison. When we measure an NMR image, we actually measure the phase, and so we measure things in K space. That is, we vary the values of K systematically, and then we do a Fourier transformation and get the NMR image. I'll show that to you. This is an image of many capillaries filled with water. And this is what we get after Fourier transformation of the measured signal. This is what the measured signal looks like. So we measure the signal amplitude, transverse magnetization, now I call it S in this case, as a function of the wave number in X and Y direction. The wave number in X and Y direction I get from applying a field gradient in the X direction and applying a field gradient in the Y direction. How we do this, we will see. So I measure the signal as a function of Kx and Ky. I do the Fourier transformation, I get the image. And I can do the Fourier transformation because that signal is phase sensitive. Now, if I would measure with scattering experiments, I cannot measure the phase. I can only see magnitude square. I can form the magnitude square of this, and I get that scattering diagram. This is exactly what you would see in X-ray scattering when you have a hexagonal lattice and you look at the X-ray reflexes, the X-ray interference peaks from a hexagonal lattice. You see that hexagonal lattice in here. Now you can say, okay, you can do the Fourier transformation of that. What you see is the autocorrelation function of the image. You only learn about the distances of the scattering centers from each other, but you never know where exactly in space the scattering centers are. This is called the Petersen function. Typically, one analyzes these with the Bragg law. You look at Bragg diffraction and you can analyze where these peaks are, and from those you know the distances. And there's a relationship that the Fourier transform of the scattering pattern is known as the Petersen function, and that is the autocorrelation function of the image. So all these things are related. NMR imaging is not just something that's separate somewhere in space, and medical people use it in the clinics, but it's related to diffraction measurements and other imaging methodology. So if you get that message, then that is at least something you can remember, and if you want to look it up, you have a way of doing that. What happened to my slide? Okay. So the next point then is, am I in the right sequence? Yes. The next point is then, how do we actually measure an NMR image? How do we make sure that we can vary K in X direction, so the wave number in X direction, or the integral of the gradient modulation function in X direction? How can we vary the integral of the gradient modulation function in Y direction? So what we need to do is we have to turn on a magnetic field, which is always in Z direction, but the gradient varies in X direction, or the gradient varies in Y direction. And we do that for a certain time. Or we do that for a given time with a certain magnitude of the gradient. So for a strong gradient, for a weak gradient, for a negative gradient. And there are two ways of doing that. Well, there are several ways of doing that. Now let me show you first an example which Paul Lauterbur came up, who got the Nobel Prize on NMR imaging, and who made the mistake of calling it a linear gradient in his Nobel lecture. It's a constant gradient, okay? It also tells you, famous people that get the Nobel Prize make mistakes. Everybody makes mistakes. So don't be shy of making a mistake. The thing is, you have to learn from your mistakes. When you learn from your mistakes, you're okay. When you make the same mistake all the time, then something is wrong. So you have to keep busy studying and improving yourself, then you don't make the same mistakes again, and you learn and you progress. So it's okay to make mistakes, but don't make them again. So it's here we see Lauterbur's method. He said, let's take that gradient and define a certain gradient gy that gives us with a certain amplitude. That's the amplitude of the gradient, and the gx has a smaller amplitude. So we know then we get a kx, which is the gradient integral, with a smaller value, and a ky with a larger value. So our resultant gradient points into a certain direction. It points in this direction. And then we can make that amplitude larger or smaller, and this larger or smaller, and this way change the direction of the gradient in cylindrical coordinates. And we always measure a free induction decay, do the Fourier transformation, and what we get is a projection of our object, or we can say in k-space, we sample k-space the signal along a radial direction. So you have to sort of get many data points in k-space, and if you have enough data points, as many data points in k-space as you want to have points in your image or pixels in your image, then you can do the math either by setting up a linear set of equations to calculate all the measured phases and the known values of k into the positions that you want to know, or more easily you do a two-dimensional Fourier transformation. Now the problem here is that to do a two-dimensional Fourier transformation on a cylindrical coordinate system is difficult. And the other alternative that Richard Ernst came up with is that one measures signals on a rectangular grid in k-space, which is much more easy for the two-dimensional Fourier transformation. You can do a Fourier transformation row by row and column by column. And the way to do that is that one does a two-dimensional experiment by turning on the gradient in y direction first for a given time, and then increment the gradient step by step in the indirect dimension. That's the principle of two-dimensional NMR spectroscopy that he makes use of here. And then afterwards he turns the y gradient off and turns the x gradient on, and then measures the free induction decay in x direction in increments, and each time you have a gradient increment from measurement point to measurement point, so your gradient integral increases proportional to the time which you measure. So during this time you measure a line in k-space, kx, that's the x gradient, and the value along ky, the value in the y direction is defined by the gradient integral, by the integral or the area underneath that gradient pulse in the y direction. And that allows you then to sample step by step all data points in two-dimensional k-space. Let me, before we take a break, do one more little discussion, because that's hard.
You mentioned about negative gradient.
Yes?
What is the significance
Of a negative, you sample negative directions in k-space. So you want to have k-space positive, is this quadrant, but you also want to have that quadrant, this and this. And a positive gradient would be when your magnetic field, this is a magnetic field, that's the space direction. That would be a positive gradient, and a negative one would be when your magnetic field gradient, when the slope is negative. So you start with a high value of magnetic field, and as space increases, position increases, your magnetic field decreases. That's a negative gradient. Just as the slope of the variation of the magnetic field. And that you can vary by the direction of the gradients and of the currents in the gradient coils. And the gradient coils is what makes the noise in magnetic resonance imaging. So if you ever had the misfortune of being in one of those machines because you're sick, you will hear a lot of noise. And that's the switching of the gradients. So you turn them on and off all the time.
So it is something that is minus x minus y, that represents negative in the machine.
No, I mean, where are they? Okay, so we'll give it a try with this one here. So a positive gradient. Okay. Well, let me. Oh, there's more. Yes. Okay, that's right. Magnetic field. Position I call it R. So you can take X, Y, Z. A positive gradient would be this variation, and a negative gradient would be this. the way how, and that direction of, I mean, there are two fields, right? The field of conducting magnet gives you the homogeneous magnetic field, and to this you add a magnetic field with coils that are driven by electrical currents, and depending on how you, I did this exercise with the, no, that was different. One current this way, the other current this way. So in series I can do it, but you do that in parallel, right? And then you get the gradient, and you change the direction now that you do this, that direction, and the other way around, then you get the gradient in the other direction. So the field varies one way or the other way. And that allows you to switch the gradient direction, and the amount of current you throw through the coil gives you the gradient amplitude. So that's something you can do by computer. And you program it on the computer, and then it does it for you. And this way you manipulate the gradient integrals, that is, you manipulate K. And you have in fact three sets of coils, one in X direction, one in Y direction, and one in Z direction. So you are able to do three directions of gradients, and you can switch gradients positive, negative, and V. Let's do the other slide later on. We have other questions. Pretty complicated stuff, huh? Very different from spectroscopy. So it's the NMR phase, that little precession angle, which you can split up into different contributions of a spin being at rest, of a spin moving, or of a spin being accelerated. And that you can measure with the different moments of the gradient modulation function. And the gradient modulation function is how you turn the gradients on and off and what values you give them. And that is, you know, the gradient integral, or the gradient times time, that integral, or gradient times square of time, or just the gradient times time to the power of 0. And you integrate. Those are the moments. That's all one does. And then you have to play it properly and figure out the different terms, that you get an image, or you measure velocity, etc. So we'll now go to examples so that all this theory becomes hopefully a little bit clearer by having some examples. Let's have some TB4 so we approach.
Sir?
Yeah?
So we are using f and g functions. We are using g function
Yes.
from Taylor's expansion.
Yes.
What that represents? What they represent? F and g functions.
What happens?
F and g functions we are using. What they represent?
G is the gradient function. That's the value of the gradient. That's the power through the current through the gradient coils.
And what about f?
F is usually taken, one usually designs spectrometers so that F is 0. Okay? But what hasn't been done yet is to make use of F. So one can make use of F. So if you are clever, you say, I want to build a simple spectrometer, or let's say I only want to measure velocity, no imaging. You can use F. And build a very simple instrument that allows you to build an NMR flow meter, for example. And then one could use F. But usually you don't find F in the normal text box because people don't even say that there is something more than the gradient. They talk about linear, and no, then they talk about non-linear gradients. But F already is the linear gradient, if you do it properly. It becomes confusing, but it's good to look at it in a clear way and then to go through that type of analysis. Okay, F typically is not important. That's why I've cut it out. But I wanted to show you it's there. So if you want it, you can make use of it.
But sometimes they mention 45 gradients, 50 gradients. So more the number of gradients, better it is.
No, I mean these are the gradient steps. And you need as many gradient steps as you have, let's say, positions to encode in the indirect dimension. And then if you have an image that has 128 pixels in one dimension, then you need 128 gradients.
So that way it is different from spectroscopy.
Much different. I mean, now your waves are in space and not in time. So we look at the magnetization function. You throw a stone in the water, and you have both phenomena. You have a wave as it spreads, the rings spread, and you see the water waves. if you take a photograph. But if you look at one position in time, you only see, how the way the water level goes up and down. That's the water weight in time. But the photograph gives you the water weight in space. And you have to look at both, in time and in space. And imaging concerns space. Spectroscopy concerns the time. T? T. Okay? Last documentation was there, right? I shall be there.
Anybody has a high resolution camera? No. A good phone, iPhone or something like that.
I found it.
You're still not coming with the train. Come over. Everybody's coming.
They're on my camera. Yeah, those pictures. Yeah, that's it. Yeah. So do they not work out well? Right.
ਤੁਸੀਂ ਕੁਛ ਕਲਿੱਕ ਕਰ ਰਹੇ ਹੋ ਨਾ ਫੋਟੋ ਵੀ ਕਲਿੱਕ ਕਰ ਰਹੇ ਹੋ ਕੁਛ ਤੁਸੀਂ
ਫੋਟੋ ਲੈਕਚਰ ਵਾਲੀ
ਲੈਕਚਰ ਵਾਲੀ ਹੈ।
ਲੈਕਚਰ ਵਾਲੀ ਤੇ ਜਿਹੜਾ ਸਪੀਕਰ ਵਾਲੀ ਤੇ ਇੱਕ ਉਹੀ ਲੱਗਦੀ ਹੈ। ਬਾਕੀ ਜਿਹੜੀ ਤੁਸੀਂ ਬ੍ਰੇਕ ਚ ਕਰਵਾਉਣੀ ਹੈ
ਨਹੀਂ ਉਸ ਤਰ੍ਹਾਂ ਵੀ ਮਤਲਬ ਇੱਕ ਦੋ ਕਲਿੱਕ ਕਰ ਲਿਆ ਕਰੋ।
ਹਰ ਲੈਕਚਰ 'ਚ
ਜਿਸ ਤਰ੍ਹਾਂ ਅਗਲੇ ਲੈਕਚਰ ਹੈ ਨਾ ਉਸ ਕਾਰਨਰ ਤੋਂ ਜਿੱਥੇ ਕਰੋ ਨਾ ਤੁਸੀਂ ਤੇ ਸਪੀਕਰ ਦੀ ਵੀ ਆ ਜਾਏਗੀ ਤੇ
ਪਹਿਲੇ ਦੀ ਵੀ ਹੈਗੀ ਹੈ। ਤੁਸੀਂ ਹਰ ਲੈਕਚਰ 'ਚ ਕਰਨੀ ਹੋਵੇ ਤਾਂ ਹਰ 'ਚ ਵੀ ਕਰ ਲੈਂਦੇ
ਹਰ 'ਚ ਕਰ ਲੈਂਦੇ ਅਗਲੀ ਨਾ ਉੱਥੋਂ ਕਾਰਨਰ ਤੋਂ ਕਰਨਾ ਹੈ ਉਹ ਫਿਰ ਤੁਸੀਂ ਟ੍ਰਾਂਸਫਰ ਕਰ ਦਿਓ ਮੈਨੂੰ।
ਹਾਂ
ਜੀ ਉਹ ਸ਼ਾਇਦ ਪ੍ਰੈਸ ਵਿੱਚ ਅਸੀਂ ਦੇਈਏ।
ਹਾਂ ਹਾਂ
grew up, I grew up in Berlin. You know, that is, again, the capital of Germany. But when I was born there, Berlin was divided because it was after the war. I was born only 7 years after World War II. And so there were many ruins, many buildings were destroyed. Life was pretty hard. Food was not easy to get. And then later on, Berlin was, there was a wall built around Berlin, the West Berlin, which was actually divided by, between the Russians, the Americans, the British, and the French. So each took one part of the city. And they said, this is ours. We determine what's going on. So we had to follow what they did, or what they decided. And then the Russians decided to build a wall around the three sectors of the Americans, the British, and the French. So that part of the city was surrounded by a big wall, a fence, much more fierce than the border to Pakistan, because there was a real wall, there was barbed wire, there were automatic guns. If you cross, you get shot. There were landmines. In fact, the cousin of my mother got killed right there when he tried to cross the border. And that lasted until 1989. So every time we wanted to leave West Berlin, there were three roads that would go through East Germany to West Germany. You had to stand in line and wait for the people, for the East German border guards. You had to have your passport. They wore big machine guns and could ask you questions. And you had to be nice to them, although you didn't like them. That was how it was. Sometime during that time, I decided to apply for a scholarship to the United States, and I was first rejected. But then I was lucky that I was sort of a substitute. Somebody decided he didn't want to go, so I could go. This is how I went to the United States. This is how I learned English. I couldn't speak English very well after high school, although I had 9 years. But I was very afraid of making mistakes, of saying something, and because I was very shy. And that's when I learned. And I did a master's degree in the United States. I came back to Germany, and we had a different education system, and people said, we don't know what a master's degree is. You do your degree again in Germany. That was different. So I had basically 2 master's degrees from the United States, from Germany. I went on for a PhD, and so that's my life story. So always work hard, and don't watch too much television, don't do too much Facebook, but rather read books, and you will be okay. If you spend your life in front of the television or just with Facebook, you're not going to get anywhere. It's working hard, and then opportunity will come, and life will be okay. So, any other questions? No? Okay, so let's get back to the science, to imaging, and again a drawing of phase space. You see kx, ky. These are the wave numbers in the 2 spatial directions. So the magnetic field gradient is applied along the x direction, here along the y direction, but we have to do that in successive, one after the other. And the scheme is shown here again, with the gradient in y direction, the gradient in x direction. But you see that these lines here. And that means every time we measure the signal basically only during the time t2, like in 2-dimensional NMR spectroscopy. Then we repeat the experiment. We prepare it with a different gradient amplitude, or the different gradient strength in y direction, and repeat again the measurement. Now, the integral over the gradient pulse, let's say that pulse, second time it's this pulse, third time it's this pulse, fourth time it's higher, fifth time it's even higher. The integral is the wave number, ky. So step by step, when we repeat that, we vary ky. And here, when we acquire the signal, kx increases automatically with time. It's always the integral of the gradient until the moment of time when we acquire one data point. So these 2 ways of encoding, people say of encoding space, with the gradients. That, for historical reasons, is called phase encoding, and that is called frequency encoding. And the reason is that when you do frequency encoding, your signal is affected by relaxation. When you do phase encoding, it is not affected by relaxation. Neither is it affected by chemical shift or other spin-spin interactions. So this type of encoding gives you higher resolution than this type of encoding. And how that is worked out is shown here. But we don't go through the details. If you like to look at it, you can look at it at home or in your lecture notes. But it is not so important for the principles that I want to discuss. I want to discuss ways how to sample now K-space. Before we had all these dots, these were the different values of K. So you look only at very discrete values of K. But you can do experiments that measure all this, the whole area of K-space, either by going through it in along a radial direction. This is what Paul Lauterbur did, and that ends up to be back projection imaging. Back projection imaging is what people do in computer tomography with X-rays. They use that type of technology. And the other way is what Richard Ernst came up and is known as Fourier imaging, is you apply first what we saw in the last scheme, in fact, on the previous slide. You apply a Y gradient pulse and then measure your signal in the presence of the X gradient. That's called Fourier imaging. Peter Mansfield, who also got the Nobel Prize in magnetic resonance imaging, came up with a complicated scheme that he switches rapidly the gradients and forms lots of gradient echoes. Just the thing to know probably is that you have to switch very quickly. And for many, many years, nobody could switch magnetic field gradients so quickly as needed. Only it took 10, 15 years until the electronics were good enough to do that. So that turned out to be for a long time just something in the box, and now it's routine for functional magnetic resonance imaging where you have to acquire images very fast. It's called echo-planar imaging. And then there's spiral imaging. There is a way to sort of go along in spirals through K-space and acquire the signal always on these traces. In each case, you have to extrapolate your data points in K-space onto a rectangular grid to do the two-dimensional Fourier transformation, and that then gives you the NMR image. So these are different imaging methods that one applies. But we will not go through these imaging methods. We will only address the Fourier imaging method in the following, because there's actually a very interesting evolution that I'd like to point out for you. But before we do that, I want to talk about slice selection. Actually, when you take an image to the human head and you want to know if you want to know basically a cross section, that means actually you slice off a part and then look at that region in the brain. So you want to measure an image of a slice through the human head. You don't want to look at a projection that sums up all the signal across one space direction. We don't want to look at a slice. And to do the slice selection was again an ingenious invention done by Peter Mansfield, who got the Nobel Prize for imaging. So with this patent, he made a lot of money. And he now has his own helicopter and flies to work if he still ever works. He's very old now. But the idea is the following. There's a three-dimensional object. Suppose it's your head or the patient's head. And you want to have a slice through the object from which you want to know want to generate the NMR image. So you want to know the image in Z and Y direction, but you want to have the slice selected in the X direction. So you only want to excite transverse magnetization in X direction, or of the slice, delta X in the X direction. So only of that particular region. Now when you apply a magnetic field gradient in that direction X, here is X, this is the direction X, and then the NMR frequency is proportional to the space axis. So that means to have a slice of the thickness delta X, you need to excite a certain frequency region delta omega in X direction. And that gives you the magnetization from that slice. So how do you look at the particular frequency region in X direction? So you only want to do a 90-degree pulse on spins in that slice in the particular frequency region, and don't have the 90-degree pulse on the others. That means your radio frequency field B1 should only be active in that frequency region. And what one does then is you want to have a B1 field, that is high in the slice and 0 outside. So the way to figure that out is you apply your radio frequency pulse in the time domain, not in the frequency domain. You want to have an excitation that in the frequency domain has that shape, and to learn about that shape you do the Fourier transformation and then you have the shape in the time domain. So the Fourier transform of that pulse is the sinc function. Now a sinc function goes from minus infinity to plus infinity. That means you need infinite time to apply the sinc function, the sinc pulse. You cannot do that because spin relaxation only works for a second and then the signal is gone. So your pulse has to be much shorter than a second. So what one does is one cuts off the lobes which continue here right and left, and then the Fourier transform of that truncated sinc pulse looks like this. And that's the approximation for the pulse you would like to have. This is what you can do in practice, and that defines the precision with which you can select the slice over here. So one always has a slice selective pulse before one does the imaging in 2 dimensions. So a slice selective pulse selects the plane of the image, and then you apply the gradients in such a way that you resolve the information of the gray shaded plane where you have selected the magnetization with the slice selective radio frequency pulse. So that's slice selection. So it's again something you will see in my notation very soon with the slice selective pulse. Now we work out one particular imaging sequence. So suppose we apply a slice selective pulse in a radio frequency gradient. So we do a gradient in z direction. So we want to measure an image in the xy plane. We apply the slice selective pulse. These are these oscillating lobes, and then we get a free induction decay. The problem is the gradient is on for a few milliseconds, and during that time the signal decays, so the signal is very weak. The signal actually starts theoretically in the center of the radio frequency pulse, so in the middle of the gradient pulse. So what one does to improve that is you apply a second gradient pulse here, which has half the area of this pulse, so that all magnetization that gets lost in the second half of the pulse, in that side of the pulse, is refocused into an echo, so you see a gradient echo and the signal becomes higher. So that's step 1. You want to have this, let's say you do an encoding by 2 wave numbers 2k, and you do a minus wave number k here, so that your total encoding is only by k, and then you see that oscillation here, because the gradient echo means that the second lobe has the same area as this lobe down here, so the sum of the 2 goes to 0, so the space encoding of that part is gone, and your signal looks as if it had started in the middle of the pulse. So you get a bigger signal. So that's step 1. We have to apply that gradient echo, what people say. Now you have to have a magnetization from a slice, and you have to introduce your frequency encoding for the y direction and the phase encoding in the y direction, the frequency encoding in the x direction. That is, you repeat your experiment many times with different values of the y gradient and record your signal in the presence of the x gradient. Again, your signal is low because it decays now in the presence of the y gradient, and you're unable to record positive and negative frequencies. You want to have positive values of k-space and negative values of k-space. So what you want to generate is an echo. So to generate an echo, you again then say, we do a gradient echo, so this area of that pulse is the same as the area of half of this pulse. And that generates a gradient echo in the x direction, and you see the signal build up and decay. Now that means you can record negative frequencies or negative time during this time, positive time and positive frequencies or positive k values when the echo decays. And the Fourier transform gives you one line in k space, or this gives you one line in k space from negative k to positive k. That's beautiful. But you're still contaminated by inhomogeneities of the static magnetic field. In fact, also susceptibility differences from the inhomogeneities of the object you want to see. Now, it only makes sense to do imaging when your object is not just the same material across the whole object. You don't need to do imaging for that. You want to do imaging because you want to see structures in your object. When you have structures in your object, it means that each structure has a different magnetic susceptibility, how it takes up the magnetic field, than the other structures next to it. But when that is different, it's the same as you have two materials next to each other that have different refraction index in optics. So the magnetic field gets distorted at the interface and becomes inhomogeneous inside the object, because only the material is inhomogeneous. So these are effects that lead to distortions and degrade your image resolution. One can get rid of that by taking a Hahn echo on top of the now you put in another 180-degree pulse here. You make the gradient echo coincide with a Hahn echo. That means also that that negative pulse here now becomes positive. And then you can record the echo train, and it now looks higher than this one because the effect of magnetic field inhomogeneity is reduced. And this for a long time was a standard method in imaging because people argued, rightly so, it gives you the best resolution. I'll show you later on some images people measured, the first images through the human head, and it becomes very obvious that this method one would want to use because the magnets just weren't good enough and the resolution was really bad. So, but an image, a medical image in those days, and I remember well, took 20 minutes. Now suppose you're sick, you're a patient, you're sitting in the magnet, and the gradients are making a lot of noise when you switch them, so they bang on your head all the time. And you have to stay quiet with your head for 20 minutes. If the resolution you want to get is better than 1 millimeter, you cannot move your head by more than 1 millimeter in 20 minutes. That's a pretty demanding situation for a patient, for somebody who is sick. Even when you're a healthy person, that's difficult. So NMR imaging was said, it's never going to be as good as X-ray tomography because it takes so long. Now you can measure an image in 20 milliseconds. So people have much faster. You can make movies of the beating heart with NMR imaging. So this is tremendous progress. And the big step in those days actually was, here is spin echo images, not medical images, just an example to show you what one can do. Some of the first people interested were people in the tire industry. Because rubber is soft, is a soft material like human tissue, tendon, brain tissue, and it is easy to image. Relaxation times are a good regime. So the tire industry bought MRI equipment, magnetic resonance imaging machines, to cut sections out of a car tire, and there are different layers in there. And you see the different layers here. That's a tire tread. There is textile fibers in there. There are different layers. And you can see how the layers, when they are vulcanized, change their molecular mobility, give rise to the contrast. And you see a bad tire here. There's a defect, in fact, in the rubber formulation. And so you could analyze the tire making process with it and optimize it so you can make better tires. So that was done by spin echo imaging, and there was a lot of innovation happened in the tire industry, not just in hospitals. And then came the idea that these imaging methods are too slow. And two people, Axel Haase and Jens Fromm, I know both very well, had the idea as PhD students, we don't need the 180-degree pulse in here. Let's go back these few slides. Here we had a sequence without the 180-degree pulse. Then that was introduced to get rid of these magnetic susceptibility field distortions, because then the image has better resolution. And everybody was so convinced, they said, we need to do this. But then you need to wait 5T1 between each scan, which is something like 5 seconds. And you end up with 20 minutes measurement time. But Axel Haase and Jens Fromm said, let's take this away and take that method. And so they went back, it took the 180-degree pulse out, went back to the gradient echo imaging scheme, slightly lower signal amplitude. And you know what? They became millionaires. They made a lot of money. They made a lot of money by taking out that one pulse that everybody was convinced it should be there. And I remember because I was a postdoc at that time, and there were trials at court and the patent office, and they sued General Electric, Siemens, and Philips, all the big MRI companies, and each of them had to pay some 10 million euros to the inventors because they now all use this method, because you could measure images in 2 minutes. 20 minutes before, 2 minutes with this method. And the reason is you don't need to wait 5T1, because that pulse doesn't need to be a 90-degree pulse anymore. It can be a small flip angle pulse, like 5 degrees. And when you only tip the magnetization by 5 degrees, you can only get a small transverse magnetization. Signal is weaker, but it takes less time for the signal to go back to the Z direction to reach thermodynamic equilibrium. And this time savings translated into 1 order of magnitude in time savings for the image, and that's why the clinics all used it. And this is how these 3 people, there was another guy was in there, got rich. There is the famous paper from 1986, and now that also allows us to look at dynamic phenomena, let's say in chemistry and chemical engineering, to do images, for example, of oscillating chemical reactions. Did you learn oscillating chemical reactions? The famous Bielousov-Zhabotinsky reaction. It's a reaction that oscillates back and forth. And some people say it's probably the chemistry that underlies the beating heart. They have a rhythmic reoccurrence of an event and is sustained then by supply of energy. These waves die out eventually when the chemistry is finished. But you see these beautiful chemical waves of chemical concentrations which move then through your container and which could be imaged for the first time as a function of time and space. So taking away a pulse, always rethinking what people tell you. Don't believe everything people tell you. Take it, accept it, that this is what they say, and then check for yourself. And only when you're 100% convinced it's right. But if you have a little grain of doubt, keep on checking. Probably even, the teacher may be as famous as possible, but they can make mistakes too. Remember, Paul Lauterbur says linear gradients is wrong. I probably make mistakes, right? Everybody makes mistakes. So think about it, and maybe you also get a million. Let's think about artifacts. We talked about susceptibility differences, and this is a very simple phantom. It's 2 glass valves, circular, one inside the other. That is filled with distilled water, and this is filled with water with some copper sulfate. So 2 water containers separated by a glass cylinder. And then we take the image, and you would expect that image. The copper sulfate has a lower relaxation time, it gives dark signal. The pure water gives a brighter signal, that's fine. This is what you expect. When you apply the regular spin echo imaging, this is what you get. This is not the circular inner cylinder as here in the drawing. When you apply back projection, this is what you get. How come? The reason is that you have internal magnetic field changes which are not refocused in the detection period when you measure your signal. Only with the phase encoding these magnetic susceptibility effects do not show up, but they show up in the frequency encoding during acquisition. So this is why you have an artifact looks different in X and Y directions over here. And this is why the artifacts appears in X and Y direction, because back projection imaging only uses frequency encoding. So it's called artifact. Artifact suggests the name, this is something bad. Artifacts, we don't want artifacts, right? Nobody likes artifacts. But then, look at this here. What that is, these are rubber sheets, and you may know that rubber is basically made sort of in a way like baking bread. You take flour and you add some other stuff, and other components, you mix it and you bake it. And rubber is made the same way. You take macromolecules, you add crosslinker, vulcanization agents, a carbon black and so on, then you mix it and you bake it. That is called vulcanization with the rubber. And then you have your rubber tire or whatever. So this was a sample where there was several layers of rubber on top of each other. And these are the same sample, but different imaging methods. That's kind of surprising that different imaging methods give you different images. But the reason is that the artifacts in the imaging methods are different. 3 imaging methods, 3 different types of artifacts. And this is a gradient echo imaging, which is most sensitive to susceptibility differences, to magnetic field distortions at interfaces. For instance, between a white and gray matter in the brain. Or in this case, between regions in the rubber that are not well mixed. You didn't knead the dough long enough. You didn't mix it well enough. And you see that. In fact, you can see even in the spin echo image different layers of rubber. But the artifacts are much less over here than here. So you may say, and actually go that way, that you say, I want to have an image with artifacts because they magnify the internal structures. And I know if there is something wrong if the material is not homogeneous. In fact, if there is a flaw in, it could be cancer in the brain, it could be an artifact or an inhomogeneity in a piece of rubber, some cluster of carbon black or whatever, which you couldn't see if you did a high-resolution image because it's too small. But the cluster of rubber has a different magnetic susceptibility, and if you sensitize your method to susceptibility differences, do gradient echo imaging instead of spin echo imaging, then that distortion shows up in a larger region than what it actually is. And then you can see it. So artifacts is a word that suggests it's bad, but you can put it to use, make use of it, and improve actually the way you see things. You make things visible that otherwise are not visible. Now another method that is quite useful, you can actually sensitize your encoding sequence by having, let's say, a spin echo period before for T2 relaxation, or another one for T1 relaxation, saturation recovery, and inversion recovery. Remember, the ways to measure relaxation: T1 is saturation recovery, inversion recovery. 2 methods. That's good to know. And then T2 is measured with a spin echo or CPMG sequence. It's also good to know. So you can put these in front of the imaging sequence and have a certain recovery of T1, of longitudinal magnetization, and then repeat with another recovery, measure many images with different recoveries, and this way measure a T1 image or a T2 image. So you can extract from the set of images the value of T1 in each volume element, the value of T2 in each volume element. Now you don't image the number of spins, what we did before essentially, in each volume element, but you image a parameter, a material property in each position. You image T2. Well, then you may ask, why is T2? What is that? What material property is it? And we did an example in Aachen many years ago. We took a carbon black cylinder and we exposed it to shear, 10 Hertz oscillation. So 10 shear deformations per second. Not very much. And that is sort of what you do when you ride a car or a motorcycle and your tire is deformed by the rotation of the wheel where it touches the road. You have a cyclic deformation, a periodic deformation of your tire. Now you may know that rubber, when it has that deformation, gets warm. It's called in polymer physics, it's the loss modulus. It tells you how much energy, deformation energy, is absorbed by the material, and that when it's absorbed, energy is absorbed means the material gets warm. And that any change in mobility is noticed by the relaxation times T1 and T2. Relaxation times are sensitive to molecular motion. If you change the molecular motion by warming the sample up, relaxation times change. So this is what we exploited. We've measured T2, we measured for different temperatures, and we find it changes roughly linearly. And is so even for different amounts of carbon black. And then we measured an NMR image and measured T2 across the diameter of this rubber cylinder. And with this curve could calibrate T2 to temperature. And this way we could measure temperature inside the rubber and outside the rubber cylinder. And clearly, by deforming the rubber gets warm everywhere, but through the surfaces it equilibrates with room temperature. So heat is dissipated to the environment, so you have lower temperatures on the surface of the rubber right and left, and higher temperature than the center. And the more rubber you have in there, it's measured in parts per 100 rubber, that's what pHR means, the higher is the absorption of energy in the rubber material. So if you have too much carbon black in your tire, then it gets warmer. But that's engineering of car tires, and people need to know that. So another way that is quite important is when you image plants. This is an NMR image, a cross-sectional image through a fennel seed or fennel fruit. And you see different images. And they're all derived from a data set acquired in this way. Now, during the detection time, TX means transmitter, RX means receiver. So we detect an echo, but all the space encoding is done in the indirect dimension. And when we detect the signal, we detect that in a homogeneous field. What is the signal you detect in a homogeneous field when they do your Fourier transformation? You get the NMR spectrum. So it means now you measure the NMR spectrum in the XY plane, and you have a slice selective pulse in the Z direction. So your image, each volume element of your image contains an NMR spectrum. Now that's cool, because there are many lines in an NMR spectrum. In fact, it looks like this one here. There's a huge water signal in there. But there are methods in NMR, especially in biological NMR, to suppress the water signal or the solvent signal. And, thank you. So you can suppress the water signal, and when you suppress it, other signals now become visible, A, B, and C. So A is, if you look at the signal A, then that gives you sort of, A, B, C, B, C, D, right. That's the image you get by water suppression. This is the signal B, that is the methoxy groups, and they tell you where all the molecules are that have methoxy groups in the plant stem, in the seed, in the fennel fruit. And C is the aromatic and olefinic groups that you see here. And when you take the water image, look at D, you see that image itself. So you can do chemical selective imaging. Look at the distribution of particular chemical compounds in a heterogeneous object like a plant, or a plant seed, or a fruit, or whatever. So that's another beautiful application. And here we go to the first medical images. There are two ways. This is a method that Demadian has come up with. He has a patent on NMR imaging. And his idea was he has a huge coil around his body. In fact, there's a picture, which I probably should have dug out, with Demadian sitting in a magnet, electromagnet, he was a big man, so he has a big body. And he had a radio frequency coil wound around his chest, and was sitting on a chair, and the chair could be moved up and down, forward, backward, right, and left. And the magnet had one sensitive spot where the magnetic field was homogeneous enough to measure the signal from. So he had to be moved through that sensitive spot point by point. And of course he was the inventor, so he had probably several hours he was sitting on the chair, and the chair was moved point by point, and they measured this image. And he was extremely proud. In fact, I remember giving him the lecture, and then he sent me the image where he was so proud of, first image to the human body. What do you see on that image? Nothing, huh? Noise. So he drew what you're supposed to see. There's the lung or the spleen, and the lung and some other stuff, liver. That's what you're supposed to see in the image, but nobody would be able. I mean, you cannot convince a medical doctor to use that. And then there were two guys at General Electric, Bill Edelstein, Hutchinson, Johnson, Redpath, four guys, and they, against the authorities or against the supervisors who told them, don't worry about magnetic resonance imaging, we have just got computer tomography to work, and this is our business line. Medical MRI will never make it. It's not a good business model. In fact, now medical MRI is bigger than computer tomography, right? It's a bigger moneymaker. So they said, well, we'll do it anyway. We'll play with it, and they had some clever ideas. In fact, they came up with a method of frequency and of phase encoding, which I mentioned earlier. Switch the gradient amplitude instead of the gradient duration. And they were able to measure these through the human head. That's a spin density image. It tells you the number of protons. What is black is bone. Less protons to see because they're solid and give less signal. And the liquid part gives it a higher signal. So you can see a lot of stuff, but it still came up with a drawing to explain what you see because the resolution is low. And they even measured a T1 parameter image. So they were able to measure the longitudinal relaxation time in each section of the brain. And that image, the fact that they did this against the notion of their superiors, of the lab director, convinced General Electric to engage in the further development of magnetic resonance imaging. And General Electric, due to these two images, then were the first ones that produced medical tomographs. So it's a very historical image, very important. And now you have NMR tomographs probably in every major clinic. So probably they have them here in Amritsar. Do they have MRI machines? Probably, yeah. See? They have them everywhere. And the hospitals in Europe or so, they have several of these. And there are separate clinics even where you just do MRIs and one after the other. So that was a revolution in science. Now, let's go to something else. Let's say we want to measure flow. And we have our chemical engineers. You remember Professor Reimer's lectures. He works with transport phenomena. You want to know the flow velocities. Maybe you invent a new microreactor or a micromixer, or you want to look at phase separation, and you look at the transport phenomena of heterogeneous fluids, emulsions, suspensions, bubbles, and so on. So you want to know how fast is a particular chemical group moving in your reactor. And you can measure that by NMR. What you need to do is you need to work with K, the wave number to encode position, but know also with Q, the wave number that encodes velocity. That's the first gradient moment. Position is a zero-order gradient moment, right? Just the integral of the gradient modulation function. And Q is the gradient modulation function times time and the integral over that. And when you do that, you can come up with images. This is a one-dimensional image. That's the space axis. That's a cylinder, and there is a fluid flowing along the z-axis. And we measure along the diameter, that's this axis, and along here we measure the velocity. So this axis is the velocity in z direction. And we actually looked at the flow of blood over here at low flow. This is measured by the Reynolds number. The chemical engineers know what the Reynolds number is. And this is a blood substitute, which is transparent. And you can actually measure in transparent fluids. You can use other methods like particle imaging velocimetry. You put little particles in there, look at the light scattering from the particles, you can measure the flow velocity. If you take real blood, you can't look inside. How do you measure velocity? Take MRI, take imaging, take magnetic resonance. And as you increase the flow velocity, the flow, this is laminar, it's a parabola, becomes non-laminar, it flattens. Well, what happens with blood is actually there's a signal loss in the center. It also flattens at different Reynolds numbers though. So it can suffer higher velocities before the flow becomes nonlinear, non-Newtonian. And the erythrocytes, the little solid particles of the blood, due to the shear motion are pressed to the side, and there you have only the plasma flow in the middle. You have the particles in the middle and the plasma on the right. This is why you have the signal over here, so the other way around. So you can analyze the blood flow. Why would you want to do this? You want to learn about blood pumps, about heart valves, and artificial devices that keep people like me alive if we get sick and have problems with our arteries and blood flow. If we eat bad food, too much fat, you get the problems, or do too little exercise. So that's when you need this, and people use that. Now this is again a thing, we went through this phase table. This is how we started at the beginning with How do we encode position, velocity, acceleration? We came up with Bayes numbers. Position was k, velocity was q. And we encode position with a single gradient pulse, and velocity with an anti-phase gradient pulse which goes up and down. 2 gradient pulses. And they define k and q. And we have to vary k and q through as many values by adjusting the gradient strength or the gradient duration, as we want to have points that then specify our velocity distribution or our spatial distribution, that is the image. And here is a pulse sequence, I don't go through the details, that allows you to image velocities, do a velocity imaging, velocity image. So what we have gradients, x, y, and z gradients. That's the only tools we have. We have to play with these. And now we have to switch them in such a way, modulate them in time, turn them on and off in such a way, that the first and the second moment of the gradient modulation function have the right values of k and q at each moment in time, especially during the detection time when we measure the echo. So that's when we measure the echo, where the line is. And you see there is kx, there is qx, ky, qy, kz, qz. So we have to encode 3 spatial dimensions for the image, and 3 spatial dimensions for the velocity vector, because it also has x, y, and z components. It's a lot of encoding to do. And you have to adjust them, and this is why the sequence looks so complicated, that during detection, the echo maximum, kx is 0, the velocity in x direction is 0, the imaging space dimension in y is non-zero, this is what you measure. The velocity in y direction is 0 because you don't want to measure it. The space direction in the x direction is non-zero, you see it here. So it changes linearly. And the z direction is 0 in space, and the velocity in z direction is non-zero, so the qz is non-zero, and it changes during detection. So you have to make sure during detection those q and k values change that you want to modulate with, that you want to retrieve information from, and the other ones are 0. And this is the trick in designing pulse sequences. Now suppose you master that, and one takes computer programs that can calculate for you, because to do it analytically is very difficult. You can arrive at things like this one, which is a velocity vector image. So you see a 2-dimensional plane, z and x, and you see vortices here, and this is rotations in a water drop that falls through the magnet. That happens when you rain, when there's rain. Why does the rain clean the air, is the question. It's a matter of principles of chemical extraction. Right? You have water drops falling through dirty air, and the water drops take up the dirt from the air. And why do they take up the dirt through the air? Because there's internal motion in the water drops. There's friction at the interface from the air as they fall down, and they set the water drops internally into motion and form vortices. And this is the vortices you see. We generated a pipette through the magnet, had a light gate that tells us when to start the measurement, and as soon as the water drop was in the sensitive volume, we did a imaging sequence and measured point by point the x and y direction and the velocity in these x and z directions, space, and x and z for velocity, to get a velocity vector image. So you have to do several images. You have to do images, with a 2-dimensional resolution demonstrated here. For example, you measure an image in x and y directions, so you encode kx, ky. You want to have velocity in z direction, you encode qz. Or you have the zy image and velocity in x direction. So you get different images, and these images then you compose into the velocity components, for example, shown here in the x and y directions, to get a velocity vector field that tells you exactly the direction in which molecules move, let's say, in a falling water drop that falls through the magnet. These are actually 32,000 drops that we had to measure. Or in a microreactor or some other technical device where you want to know the streamlines of flow inside your device. And that is called flow imaging. So I think this is where I need to stop. There are other methods that you will find in the manuscript where you can just measure flow and flow distribution. So what is the probability in a pipe to have a certain velocity of flow without knowing where that particular streamline of flow is within the pipe. So you can do that without position encoding. Just measure distributions of velocity. You can also measure distributions of acceleration. You can do that in 1 dimension, you can do that in 2 dimensions. There's a tremendous wealth of generating information on dynamic phenomena if you're can apply cleverly these principles of K encoding for position and Q encoding for velocity. Many, many different combinations possible. A very rich field for use in chemical engineering, but also, of course, for use in the medical sciences to look at the blood flow through the beating human heart. So I hope that gave you a little bit of an idea of magnetic resonance imaging, the concepts behind it. So if you have any questions, feel free to answer. Tomorrow we will do materials testing. We do relaxation and diffusion, NMR, without spatial resolution. So we go back to material science. Today was imaging. And I thank you for your attention. And please ask questions. It was difficult and there must be questions. So I look forward for some good questions. Questions? Stuff on. So it's position encoding, is position that you measure with one gradient pulse that gets your image. And the different ways of doing that with frequency and phase encoding, not so important. And if you do gradient pulses, one up, one down, you measure velocity.
How rain extracts the dirt from the raindrops?
You have a water drop. Water drops, by the way, are mostly spherical. They are not sort of like, a tear or so one finds in drawings. They're roughly round, maybe a little bit distorted. And then there's a surface tension around the drop that keeps the drop as a drop, right? So the water doesn't evaporate. And when it falls down through the air, if you would sit in the drop, then you would see the air streaming up on the sides. And there is friction between the air and the surface of the drop, which means the molecules from the drop, they are moved upward. But since they can't leave the drop, they have to curve inside. So they do a vortex motion with the air streaming up or the water drop falling down, and this way the friction makes the molecules from the surface of the drop go inside and form this vortex motion. And along with it, they carry the dirt from the air. So they take that up at the interface. And that dirt of the air actually settles at the bottom of from the falling drop, it settles on the surface or the top of the drop when the drop falls. And this way, the impurities, the dirt, settles in one part, and these vortices have less part to develop, and they become smaller and smaller and smaller until they die out. This is how water cleans the air. It's a very complicated process used for chemical extraction, extraction columns, bubble columns that work on that principle. And chemistry knows how to make use of that in chemical engineering. Same principle. That you can study the details. In fact, we had a large project for many years to build devices and then study, do the measurement data and then give them to the chemical engineers to simulate, because they wanted to know. So it was worth, a lot of money just to understand that particular process. It's a big issue.
It also measures the size of the drop.
Oh, the size of the drop is relatively straightforward, because you, once you know the strength of your gradients and the strength of your, how you vary your gradient, then you can, from those parameters, vary the size of your drop. In fact, there's a good way. You put in an object of known size, and in this way can calibrate your gradients in the image. That you know then the gradient strengths, because there are relationships which I didn't go into, but I showed them briefly on the screen, that allow you then from the total dimension that you have, calculate the strength of your gradient.
Because if I'm correct, then the rain starts when the drop, it becomes this particular size.
Oh, yeah.
So is it possible to forecast
We have not looked into this. I mean, then you need very small drops, and then you need very high resolution imaging. When you have high resolution imaging, you need very large data sets for the image. And probably the size, you would probably see relaxation effects as a result of the size. Because the surface molecules will experience a different relaxation than the bulk molecules in the center of the drop, and that will affect the relaxation of the surface versus the bulk. And the smaller you drop, the more will the surface molecules dominate the relaxation. There, in fact, has been recent work on looking at sprays and seeing the distribution. So basically, you look at very, very tiny water drops like in fog coming out of a nozzle, and one can image the distribution velocity of these spray water drops. Was done by the group in New Brunswick in Fredericton. So that is doable, but not that you resolve individual drops, but you look at ensembles and measure the relaxation properties of ensembles. From there you should get that.
It may be a silly question to ask, but can we use NMR, the high magnets, to stop the cell division, rapidly cell division, as in case of cancer or tumors? Is it possible?
I haven't heard of that. I mean, there are magnetic field effects on chemical reactions, and especially in electrochemistry, but also, of course, on the conductivity of nerves. I mean, this is why in the very high field MRI machines, you have to put in the patient very, very slowly, so that the induced currents in the conducting tissue are not too strong. Otherwise, you get a headache, you get dizzy, or you may even become unconscious. But that these effects are so strong that they have an impact on the cancer cells, I haven't heard yet. Probably, but you know, it's an interesting proposition. But probably if you combine that with electrodes, you expose them to a voltage. That might work, but then you have to be careful that the current is not too high and the patient dies from other causes. So it's an interesting field. It may not work in medicine, but it certainly may impact the way one conducts chemical reactions. And you find alternative routes to synthetic chemistry by applying magnetic fields and electric fields in proper ways. No. I mean, there are stories, clinics that say that the healing of bones proceeds faster with magnets. In fact, if that is really true, I mean, it is sort of like a homeopathic medicine. You believe it or you don't believe it. I mean, but the scientific evidence is not there that there is proof that homeopathic medicine works. It's a personal thing. If you get better and you take it, that's great. But as a general prescription, there's no proof. And there's also, we live in Aachen, and Aachen is known for horses and competitions and so on. And people are there that sell magnetic blankets for horses. So they have big blankets, and there are hundreds of little magnets sewn into the blanket. And the idea is you put it over the horse, and the horse performs better in the race. But I mean, this is incredible nonsense. Because what happens when you have lots of magnets next to each other, they always align so that the magnetic field cancels. So you spend a lot of money on nothing, because the magnetic field cancels. That's how the magnets align. And the horse, other than wearing a heavy blanket, doesn't have any benefit. But there's lots of people that sell you stuff, and it doesn't have to be good. Yeah. Other questions? Also general questions? Questions from the other lectures, maybe? We got time. Okay.
If there is no question, that is the end of lecture for today. So we will tomorrow at 10 o'clock.
मेरे को